I guess I'll go through the few announcements we have. So, of course, all the announcements are here. Again, thanks for completing the mid-semester survey. That was very, very good. I think a lot of you responded, so I appreciate that. The next important announcement is here. So let me just reiterate this. This is an opportunity for you to actually talk with experts in the field of commercialization and try to get some experience, get some feedback from experts. So I have detailed instructions here, so let me just go through that fairly quickly. So you can, if you click through, you'll see, and I kind of try to write out detailed instructions. First of all, each team has been assigned a mentor, and most of the mentors are from the Technology and Venture Commercialization Office, and their emails are here. What I need you to do is one person from the team should serve as a contact person and contact your mentor. So for instance, let's say Evan will is the contact. Let's say he'll email Paul at this email and try to schedule 2 meetings. So literally there are only 2 meetings you have to do and roughly an hour each. And that's described here. And of course, all the team members should be present at the meeting. But you can do the meeting remotely if you have to. I know schedules are hard, so that's fine. So that's one. And the 2 meetings are described here. So you need to set up your first meeting during the week of November 12th. I suggest doing this after the class on November 13th, okay, because we would have done a business canvas by then. So, but if you can't, that's okay. And there at that meeting, you'll present your technical innovation, which is your assignment 3 that you're working on right now. And if you wish, your previous assignments as well, so you can give some background. And I would say an early version of the business canvas. This is something we will do in class on November 13th. So you can plan accordingly. The goal is that the mentor will give you feedback on both of these and also provide guidance on how to develop a business plan, which is your final assignment. Okay, final 2 assignments actually. And then you should try to incorporate this feedback as you start working on assignment 4 and the final submission. Then you get to do another second meeting. This is the week after Thanksgiving. You will basically present an updated version of your business canvas and a close to final business plan presentation, which is your assignment 4, and that will be due the following week. So it'll be kind of rough, but that's okay. The goal is to improve it. And the mentors, again, will give you feedback, and then you incorporate them. Okay. Also note that the mentors will likely attend your final presentation on December 6th and provide input for grading. So if there are any questions, let me know. Of course, email me or the TA. But I think it's fairly clear. So anyway, that's one. The second announcement I wanted to make is that I also gave instructions for assignment 4, which is due December 6th, and the final submission. The final submission involves 3 parts. There's a business plan, which is only 2 pages. There's a business canvas and a video, a very short video, less than a minute, a couple of minutes, all are due December 7th, okay? And the instructions are here. I won't go through it right now because there's some detail we haven't covered, but for those of you who want to think ahead, it's all here and you can read through it, okay? Okay, we'll come back to that later on. So I just wanted to point out those things are there. Okay, so today, just take a quick look at the schedule. Make sure we're clear. Today we're going to talk about spectrum splitting. The lecture notes are here, and let me point out a useful reference paper is here. I would recommend you take a look at it if you're interested. It's a paper in Nature Materials by a group from Caltech. They talk about photonic design principles for high efficiency photovoltaics. So it's a very interesting paper. Talks, about these ideas from a thermodynamic perspective, which is quite useful and different. Okay, oh, one last thing I should also point out. In this month's journal Optics and Photonics News, there are some very interesting articles that came out, and I'm going to try to post them. So let me see if I can. I'll just show it very quickly. Let's see, where is it? Maybe I closed it. I can't find it now. But anyway, so I'll post it online and you can take a look. There are some interesting articles on daylighting, basically. So for the group that's working on daylighting, this would be a very useful reference article to look at. Okay, so let's just jump right in here. What's that? Okay, so today we're going to focus on spectrum splitting, but specifically we're going to focus on diffractive spectrum splitting. So, which you will see what I mean by that, and the primary reason for that is this is some active research that was going on and is still going on in my lab, and a pretty interesting area for you, where a very relatively simple optical technique is used to improve the efficiency of solar cells. Oops. So our motivation, of course, is to increase the adoption of solar panels, okay? And then the question is, okay, what is the fundamental limitation to prevent this widespread adoption? And one important thing that comes up is a reduction in cost. So almost everything, most of research, at least on the engineering side for solar cells, really is trying to address the question of cost. And then we have to kind of address this question, okay, where are the costs coming from? Like, how do photovoltaic costs break down, right? And approximately it's as follows. This is a couple of years old, but it's pretty representative. You have actual module hardware costs, which is a little more than 50%. Okay, so this is basically the glass, the aluminum, the silicon, all that kind of stuff. Electronics, well, the power electronics is separate. It's a smaller slice here, which includes inverters, all the wiring, all that, maybe, yeah, that kind of stuff. But you will see a very important chunk of this cost, almost, I would say 40% of the cost is actually installation and BOS. BOS refers to balance of systems and refers to things like transportation costs, licensing costs, regulatory costs, things like that. So that's a pretty big cost, right? You have pretty high labor costs for installation. You need electricians and things like that. So, a lot of people just focus on the module, which is of course a big part of the cost, but and tend to ignore this part. But I think what I want you to think about is this is also an important part of the cost if you're trying to think about, okay, how do I use optics to
your audio is
okay.
Weird now.
Can you hear me?
Yeah, something happened.
Can you not hear me?
Now it's good, yeah.
Okay, that's weird. I didn't do anything, but so what I mean to say is that when you start thinking about how in optics, how can you make a difference? Of course, you can think of, okay, I can reduce the module cost. For instance, by using a concentrator, I can reduce the size of the solar cell and reduce that cost because concentrator is cheaper than the cell. But how can I also address this cost? That's the question. And an obvious answer to that question is I can reduce this cost if I increase the efficiency of the entire system, right? And this is common sense because if I can install let's imagine I want 100 kilowatts, okay? And I can get 100 kilowatts with a low efficiency solar module, but this will be, let's say, low efficiency, so I need, let's say, 100 of them. Whereas if I can double the efficiency, I only need 50 of them. That means I can reduce the installation costs. And that can make a huge difference. So this is why the efficiency is very, very important. It has actually been quantified. A very simple analysis is shown here. So this is the impact of balance of systems and how it varies with module efficiency. This is from 2009, so it's a little bit dated, but it's a good analysis to think about, right? So this plot plots the cost, dollars per watt, direct current. So this is basically, think about this as, imagine it's a battery being charged. Okay, that's roughly the cost of charging a battery per watt. And that's the efficiency of the solar cell. And these are different curves. So let's look at one curve, let's say residential solar, which is, we're all familiar with somewhat. So that's this blue curve here. So what, first of all, you can see as you increase efficiency here, this is dropping, right? So the dollars per watt drops. Because why? Because the dollars per watt includes a cost of the module plus an installation cost. That installation cost reduces with the increasing efficiency, as I just mentioned to you. So of course, after a while it saturates, so there's some asymptotic effect here. And it also depends on the application. So if you have a commercial system, if you have tracking, non-tracking, two-axis tracking, high concentration, and so on. So you can see the best case scenario is this non-tracking ground in this particular situation. Of course, all of these plots will depend very much on the assumptions, right? The cost assumptions and so on. But a really interesting conclusion can be drawn here that if you look at the example at the bottom, a 5% efficient module costing nothing, so it's given away for free, would have essentially the same system price, $3.50 per watt, for residential rooftops as a 15% module costing about $1.50 per watt. So that's a very, very interesting analysis, right, if you think about it. Let me just repeat that. So if you take a 5% efficient module, okay, and residential, that's what it costs, $3.50. Okay, and let's imagine that's basically given away for free, right? That will be equivalent to a 15% module, okay, which has a cost of, let's say, about $2 plus $1.50 for the cost of the module itself. So that's pretty, I would say, remarkable if you really think about it. So the point I want to come across here is, from a purely economics point of view, increasing the biggest bang for your buck that you can get is by increasing efficiency. So it's a very, very important parameter to think about. By the way, this is one of the reasons why very low efficiency thin film solar, it really never became commercially successful. Compared to silicon. I mean, there are still some niche applications, but it did not get widely adopted after several decades of trials. This is another way to look at the same, roughly the same information. Here we're looking at the what's called the levelized cost of electricity on the horizontal curve. This is basically the cost of electricity that we pay.
Your audio again. I don't know.
Let me see.
Yeah, now is good.
Let me quit some things.
No, it's like something's hitting on the laptop, or I don't know.
Okay, I'm not touching it, but
No.
well, just let me know if it's not clear. So the levelized cost of electricity is in cents per kilowatt hour. And this says the constant dollars, that just means inflation hasn't accounted for it, not so important for us. But this is the number that you will see if you open your power bill. So Rocky Mountain Power, if you look at your bill, you'll see something in cents per kilowatt hour. Kilowatt hour, of course, is energy as opposed to watts, which is power, right? So it's different. Power times time is energy. So here you can see how the module cost affects the cost of electricity. So the module cost is in dollars per meter squared, is shown on the vertical axis. So the higher the efficiency, the more vertical the curve becomes, right? In other words, the cost of electricity becomes less sensitive to the cost of the module if your module is very efficient. And that's a good thing. And the opposite is true on the other end, right? And for planning purposes, general natural gas or coal-powered electricity costs roughly, it depends on the state, of course, but roughly from 3 to 6 cents per kilowatt hour. So a 6 there is a good planning target for most solar cells. So another way to look at this curve, by the way, is let's say our target is 6 cents. That means if I only have a 10% efficient module, I need to sell that module very, very cheap, right? About $10 per meter squared. Whereas if I have a 25% efficient module, I can actually sell it for about 10 times as much. Sorry, about 6-7 times as much, right? $120 per meter squared. So that's, of course, a big difference, right? Big economic incentive. Okay, so then the next question to ask as engineers is, okay, what limits the efficiency? Like, why is the efficiency only 10%, right? Or 30% or whatever? What is limiting it? And the most important thing that limits it is the fact that a single band gap does not match the solar spectrum. So in other words, if you look at the solar spectrum, it's very, very, very broad, but a single band gap material can only absorb so much of the light. Okay, so here, for instance, we split it into multiple bands here, and you can see how they're spread out. It goes all the way from ultraviolet to blue to green, yellow, red, orange, red, and infrared. Right. So how does this affect the efficiency? Where does the energy go? So let's try to understand what happens as the light comes in. So if you have a photon that comes in, it has a specific energy of h nu. We have a solar cell, which is a semiconductor, which has a valence band and a conduction band. And if the photon, and you'll learn more about this in the next lecture, and the valence band and conduction band are separated by what's called the band gap, Eg. Now, the valence band, of course, is characterized by filled energy levels, completely filled with electrons, whereas the conduction band is characterized by empty energy levels. We call them holes, but let's imagine they're just empty levels. As soon as a photon comes in, various things can happen. If the energy of the photon is equal to that of the band gap, then it will get absorbed with high probability, let's say, and the electron gets kicked up because the electron gains that energy from that photon, and essentially goes to the conduction band. So potential energy essentially increases. Okay, now it's free to move around. Okay, so it exhibits both kinetic energy as well. So there's some interesting physics there, but we won't go into too much detail. The second thing that can happen, what happens if the energy of the photon is less than the band gap? Is nothing. The photon is not absorbed. It just passes straight through. Okay. Of course, if the photon is not absorbed, then there's no chance of creating a current. So we call this a loss, right? It's a non-absorption loss. Then if the photon energy is larger than the band gap, you also end up with a loss, because what happens is that, let's imagine the photon energy is much larger than the band gap as shown here. Then an electron from deep inside the valence band gets excited deep into the conduction band. But unfortunately, and creates this electron and a hole pair. This absence of an electron in the valence band is called a hole. However, because they're so far from the band edges, because of some quantum mechanical reasons, they very, very, very quickly relax to the band edge. That's shown by these red arrows. Okay, and that relaxation essentially happens by losing energy, right? You go from so high up, so the vertical axis is energy here, to somewhere here. Okay, so you've lost this much energy, and same thing happens here. So vertical axis increasing energy for the electron, vertical axis decreasing energy for the hole because of the sign difference. The potential energy changes. But not terribly important for you to appreciate it. But the key point is that if the energy of the photon is much larger than the band gap, you end up losing a significant fraction of the energy as heat within the crystal of the semiconductor. And this is called a thermalization loss. Okay. You can also have a loss which is related to what's called radiative recombination. All that means is that an electron which is here, once it has reached here, can, instead of reaching the terminal and forming a current, which is not shown in this diagram, it can simply come down to the valence band and recombine with the hole, releasing another photon. So even though the photon is absorbed, it just gets re-emitted and no current is produced. And this is called radiative recombination. So all of these things can essentially reduce the efficiency of even the most ideal solar cell. Okay? And these are the fundamental reasons why the efficiency is not 100%. Now, the next question is, okay, how do we quantify them? Like, how much do these losses mean in terms of percentages? And that's what's shown in this diagram, which is extracted from the paper that I mentioned from the Caltech group. So here, let's imagine we start with 100%. Okay, where does the energy go? So, and in a conventional single junction solar cell like silicon, the best you can do is shown by this green curve, bar here, which is about 30%. Okay, everything else is lost. So we want to try to understand where is it going. Okay, we start first with the big loss, which is this big rectangle here, which is the energy loss due to thermalization and lack of absorption, which is these two things we talked about. Okay, so that by itself basically gets rid of maybe 30–40% of the light is gone. Okay, and everything else is smaller things, so we can go through them. So there's an energy loss in the Carnot cycle because of the temperature difference between the sun and the solar cell. We know that from thermodynamics. And there's a whole hot region and a cold region. There's a efficiency limited by the Carnot theorem. Then there's an entropy loss due to absorption or emission. This is a kind of a tricky thing to explain, but again, comes from the second law of thermodynamics, but won't go into the details of it. There's another entropy loss due to non-reciprocity, which basically means that the sun emits in all directions, but the solar cell only accepts a certain acceptance cone. So there's also some sort of an entropy mismatch there, referred to as non-reciprocity, that leads to a loss of efficiency. And then there's an entropy loss due to lack of angle restriction. Again, it has to do with the fact that re-emission of light from a solar cell is restricted because of the higher refractive index of the material. And then there's a smaller entropy loss due to incomplete light trapping and reduced quantum efficiency. So all of this basically includes things like surface recombination, as we talked about in the last class. The net result of all of this is the fact that the best you can hope to do is about 30% with a single junction solar cell. Okay, and that's pretty low, right? If you think about it, you've basically thrown out 70% of the light. So then the next obvious question is, what can we do about it? Is there any way to kind of address this big loss mechanism, right? This big rectangle here. Because that's not a fundamental loss mechanism. It's only fundamental because we're talking about a single junction solar cell. We can actually address some of this. And that's what we're going to talk about with spectrum splitting. One obvious way to, or historically obvious way to address this is what's called multi-junction solar cell. So what that means is that you basically stack different solar cells on top of each other. So you have what's called a top cell. So let's focus here, indium gallium phosphide, which is a high band gap. Then there's a middle cell, indium gallium arsenide, which has kind of a middle band gap, slightly lower than this. This 1.4 eV is band gap. EV, of course, is electron volts. We talked about this before. And then there's a bottom cell, which is germanium, let's say 0.65 eV. Now, what does this do? The highest band gap means that any photon that comes in needs to have high enough energy to be absorbed. Otherwise, it will pass straight through. There's no absorption, right? So if you look at this plot, which is our solar spectrum, this is wavelength, this is spectral irradiance, watts per meter squared per micron. The highest energy photons are in the left-hand side, these blue photons, right? These photons will get absorbed in the top cell, indium gallium phosphide. That's why it's shown in blue. Everything else passes straight through. The next set of photons, shown in green here, gets absorbed in the middle cell. Everything else passes through. And then the last set of photons get absorbed in the last bottom cell. And everything else, of course, passes through. So now we have avoided quite a large chunk of the non-absorption and the thermalization errors. Okay? So this is one clever way to essentially increase the efficiency. In fact, the the current world record for efficiency is held by a cell like this. In fact, it has 4 cells, actually 4 layers. You can ignore all the details here because these details have to do with the p-n junction, which we'll talk about in the next lecture. Not terribly important for us. But the world record is held by a 4-cell device with very high concentration, and the efficiency there is maybe like 41, 42%. And I believe it's held by an institute in Germany today. However, the big challenge, so these cells are commercially available. They are used quite commonly in space where the cost is not so important, but the weight is important. So, and the efficiency is important, right? So you can only put so many solar panels on your Mars rover. So you want it to be as efficient as possible, but you're willing to spend a lot of money for that. So that's where these types of devices come into play. They tend to be quite expensive because they require all these exotic materials. They also suffer from things like lattice matching. So this is a very fundamental problem where you're trying to put a material like germanium underneath a material like indium gallium arsenide, so their crystal structures don't really match. So what ends up happening is that one crystal looks like that, another crystal looks like that. There's a defect that happens here. So at these defects, essentially electron holes can be captured, and then they don't contribute to current, and they cause reduction in efficiency. And they tend to be very, very hard to get rid of. We also have to do current matching. So one interesting thing you might notice is that this cells can be thought of as 3 different batteries, right? They're all connected in series. In other words, they all have to have the same current flowing through. You add the voltages. So that means the current produced by each cell must be the same. So that's problematic because, as you can see in this curve, sometimes you have a lot more photons here than here, right? The number of photons, of course, determine the current. So that means some cells might be operating at not the optimum point. So that's what's shown in this curve. So here, if you want to current match these 3 different cells, the top cell might be producing this much current, middle cell might be producing this much current, but the bottom cell is producing a lot more, but we actually have to not allow it to produce that much and reduce that current, which is of course an artificial loss, right? But we don't have a choice because they're all connected in series. And the materials are expensive. So I think I'm not going to ask you to do this brainstorming session, but I want you to think about this as a take-home homework for you. Just think about it yourself. It's how would you solve this problem? And there are many solutions to this problem, and I'll talk about one particular one. So again, the problem we're trying to solve is we want to reduce the amount of light that is lost by non-absorption and the energy lost by thermalization. So we want to match the absorption of the solar cell to the incident spectrum. Okay, so that's the problem. So let me go through our solution, where what we do is we define an optical element, which is, you can think about it as like a concentrator. We call it a polychromat, but the name's not that important. There's sunlight coming in, and it's like a Fresnel lens, let's say. It concentrates the light onto 2 solar cells, let's imagine. Okay? One solar cell has the blue one has higher band gap than the red one. So we take all the high energy photons and send it to the blue one. We take all the red low energy photons and send it to the red one. And then we avoid or minimize the non-absorption and thermalization problem. Now, of course, because these 2 cells are now sitting next to each other, they need not be connected in series, right? So they can operate it completely independently. So in this situation, you can have 1 terminal from the red cell, 1 terminal from the blue, 2 terminals from the red cell producing current, 2 terminals from the blue cell producing current, completely independently of each other. Okay, so that's the advantage. So it's a relative, and if you can make this optic really cheaply, like a Fresnel lens or something like that, then this whole system can be overall quite cheap. That's the vision. However, to do this is hard. So one of the first things, I won't go into the details of how this works, but we use a diffractive element, and whose design is fairly complex, as shown here. So they consist of little grooves that are etched into a dielectric material, and they're fairly complicated. So if you zoom into this region, it looks kind of like that. They're fairly small, about 10 microns, but in this example. And they are not very deep, about 1.4 micron in this example. And what light does is shown in the simulation, where the vertical axis is called wavelength, and the horizontal axis is position or space. So you can see all the short wavelength, high energy photons, which are concentrated on the left-hand side, and the low energy photons are concentrated on the right-hand side. So we call this the band 1, and this is the band 2. So by putting a solar cell here, you can absorb, with high band gap, you can absorb all these photons. Putting a solar cell here with a lower band gap, you can absorb all these photons. There's a little bit of crosstalk, as you can tell, which is of course problematic, but that's the reality of designing these elements. The optical efficiency is important. So the way we define optical efficiency in this case, it's similar to what we did for the CPC, but here we think about efficiency as what is the probability of a photon to end up on the right solar cell, right? So you want the low energy, high energy photons to end up on the left-hand side. So this, the efficiency here defines the probability that a photon of enough energy, let's say 450 nanometers, ends up on the left-hand side. It's about 80%. Okay, so and it goes, it's high on the for the high energy photons, and it decreases for the low energy photons. And the opposite is true for the other side. So you have two efficiency curves. Okay, and then you can average them and get an average efficiency of 74% over all the wavelengths of interest. So of course, the efficiency is not 100%, and the reason is that some of the light, of course, goes into crosstalk, right? Like you'll see some of the light ends up here, which is not supposed to. Some of the light is also reflected off the top by Fresnel reflections and so on and so forth. So we can, let me show you just some examples of an actual device. So this is a microscope image of one of these devices. They are, of course, microscopic. They're made of little grooves. They look like gratings. And if you look at a 3D image, they look like this, piano keys, so pretty interesting. And they have multiple heights, as you can see. And all we do is illuminate this with the sun, and the light will simply diffract. Okay. Let me just mention briefly how we make them. We make them using a technique called grayscale lithography. And the idea, actually, before I go into it, is to make a master pattern like this, then make a hard hard replica of this, and then use that hard replica to essentially stamp out plastic versions of this device. Very similar to what happens in a DVD production or a CD production. So the master itself is made with grayscale lithography, where we use a focused UV laser beam, and its energy from the laser beam is changed. So low energy here, higher energy, and higher energy here on a photoresist on top of a glass substrate. And after development, after the lithography process, you end up with these different height levels. So by controlling the energy of the light, you can change the height of this part of the resist that's removed. And
there is a question.
Yeah.
There's a question.
The UV source, is there multiple UV sources, or is it just one that's being moved?
It's one that's being moved. In fact, what happens is that you move the substrate. This is a single source, yeah. So for those of you who might be familiar with the nanofab at the U, this is the Heidelberg Instruments pattern generator. That's what we use. Oops. So at high volume manufacturing, we can essentially do this in a roll-to-roll fashion. You basically have a foil and a polymer foil, which is rolled through a roller, And then you have an embossing drum which has the pattern on it, which is essentially rotated around this drum. And there are heating plates which soften the polymer, and then it's pressed in, and then it's replicated on this side, and then it can be laminated onto a substrate if needed. This is very similar to the processes used today for embossing of holograms used in packaging, or also printing of currency notes, newspapers, and things like that as well. So kind of relatively simple, low cost, high volume process. And the way one can imagine using this, although this is not quite, our particular device is not in commercial production yet.
Your audio is doing something. Yeah, now I think it's good.
Okay. Although our particular device is not quite in commercial production yet, you can imagine using something like this to make large arrays of these devices and combine them with arrays of solar cells to produce high efficiency solar energy. I'll show you a few more examples of experimental results using this device, so you can see how these things look like. So this is also a good example of a solar simulator. So we have a lamp here, which is our very, I would say, poor man's version of a solar simulator. And there's some optics here simply to collimate the beam and clean the beam. And we achieve quite a bit of uniformity simply by allowing the light to travel over a very long distance. So this distance from here to here is approximately 1 meter. So we're going through roughly 3 meters to reach the device, which is here, and the solar cells are placed behind it. If we look at the device itself, that's what the polychromat or the solar concentrator looks like. We have you see 3 repeat units here, which is basically the 3 units, 3 periods. So as I said before, we can make large periodic arrays. We only made 3 here. And the light is illuminating, and you can see 3 periodic patterns here. This is just a piece of white paper, so you can see the colors. And if we look at the colors more closely, we'll see that they repeat about 10 millimeters. So our solar cells have to be 5 mm. That's why this was designed this way. The visible bands are, of course, very bright, very clearly visible. The infrared bands are very dark. You can't see them. So here we're splitting the light between visible and the infrared. Okay. And then we actually characterize this light. We want to understand what are the wavelengths at each of these locations. In order to do that, we can simply put a spectrometer at this location and measure the spectrum. And that's shown here. So that's a spectrometer, an input, fiber input to a spectrometer. So that fiber goes to a spectrometer like that. And this fiber is held at the image plane, which is the same plane as here. And then it's scanned very, very precisely on this micrometer stage. In this example, it is done manually, so you turn that screw, okay, and the device is again here. This distance between the polychromat and the spectrometer is set by this millimeter stage on a track. So you can see the distance. This distance is fairly large in this example, but it can be small depending upon how you design it. Once we do those measurements, let me see, what you end up with is something which looks like this on the right-hand side. So, move that out of the way. So this, again, this corresponds to the simulation. So the wavelength is shown in the vertical axis. The position is in the horizontal axis. And again, as we saw before, the high energy photons end up on the left-hand side. The low energy photons end up on the right-hand side. And indeed, in the experiments, that's exactly what we see. So you can see the experimental data, the high energy photons on the left, low energy photons on the right. There's a little bit of smearing of the data, which you can see, of these lines that are not as sharp as this. And some of that is because the fiber has a finite aperture. So you're kind of averaging over in space a little bit. So it gives you a little blurring here. But nevertheless, the agreement is quite remarkable. If you look through this carefully, which is good. That's all we want. So the next thing after this is we want to put a solar cell here, another solar cell here, measure the current voltage characteristics, and make sure we're getting more efficiency than before. This is just the optical efficiency, so you can measure the optical efficiency compares with the simulated optical efficiency. They're pretty close, yeah. So that's expected. So it's not too surprising. The integrating the electrical properties are pretty one thing to keep in mind. So this is a good example of how do we do an optical design where we account for the electrical properties of the cells. So in this example, we're looking at a gallium indium phosphide cell whose external quantum efficiency, which we talked about in the last lecture, is shown in this blue curve. So this is a measured external quantum efficiency. We measured it exactly like we described in the last lecture. This is the red curve is the gallium arsenide external quantum efficiency. So you will see that the gallium indium phosphide has a higher band gap, so it cuts off right there, right, than gallium arsenide. So our goal is to combine gallium indium phosphide and gallium arsenide to get more efficiency. So you want to capture the high energy photons with gallium indium phosphide, the lower energy photons with gallium arsenide. We can do this. First, we do some reference electrical measurements. So this is without any spectrum splitting, just with the source. We measure the current voltage characteristics, again, exactly like we described in the last lecture. The voltage biases the gallium indium phosphide cell, measure the current. This is current densities plotted here, which is milliamps per centimeter squared. These curves are actually not very good. You can see that they're not very square, right? The fill factor is somewhat low. And the cells are actually very good. These cells are not commercial cells. These are research cells provided by the National Renewable Energy Labs. The measurements were done in my lab, but the reason the curves don't look so good is because the light is very, very low. Because remember, we had to let the light propagate over a very, very long distance. So the amount of energy, that power that's hitting the cells is quite low, which ends up causing these relatively poor quality curves. Nevertheless, you can notice two different things here. First of all, the gallium arsenide open circuit voltage is higher than the open circuit voltage of gallium indium phosphide, which makes sense. Actually, wait a second. Oh no, sorry. The open circuit voltage is here. My mistake. The open circuit voltage should be 0 current. It's here. So you can see the gallium arsenide open circuit voltage is about 0.85. Gallium indium phosphide open circuit voltage is a little higher, closer to about 0.95. Okay, that makes sense because the band gap of gallium indium phosphide is higher than that of gallium arsenide. The other thing you'll notice is that the short circuit current density of gallium arsenide is higher than that of gallium indium phosphide. And that also makes sense. Why? And that's, you can see from the EQE, the gallium arsenide captures more of the spectrum, right? So there's more photons there, which is producing more current. But it's producing all that current at a lower voltage. So not the most efficient way to produce it. So current is higher, but not the most efficient way. Then this is just another polychromat design. I won't go into much detail here, but this is what it does. It's the wavelength is flipped here from the previous curve you saw, but the high energy photons are on the left, low energy photons on the right. This is supposed to be gallium indium phosphide to be placed here, gallium arsenide to be placed there. This is just the efficiency. So you've seen this before. It just looks nicer than before. It's a better design. We can also simulate, of course, what to expect in the electrical measurements. So gallium indium phosphide, we have a reference measurement without any spectrum splitting. And what happens if you have ideal spectrum splitting, you expect the current density to go up. Because why? Because you're concentrating the light, right? Remember, in the schematic, so let me just point this out. It's an important point. Up here, in the schematic, you can see, let's imagine this is gallium indium phosphide, that's gallium arsenide. If I don't have this polychromat, I'm only going to collect this much of the light, this much area. But because I have the polychromat, I'm collecting this much area, right? So I'm actually collecting a lot more light and concentrating it. And when I collect more light, I have more photons. Of course, my current density should increase. And that's represented in this simulation. The physics makes sense, right? I expect that current density to increase in both cases, both for gallium indium phosphide and also for gallium arsenide. For gallium indium phosphide, I expect a larger increase because I'm essentially I'm starting from a lower number, and I can essentially double it. It's not exactly double because I have some efficiency losses, even for an ideal polychromat. In other words, I have some optical losses from this concentration, right? It's not 100% efficient like a CPC. In the gallium arsenide, you see a smaller increase. The open circuit voltage increases also slightly. That has to do with a more complex reason, so I won't go into the details, but it increases by a logarithmic factor of the concentration. You can also look at the power voltage curves, which is current power density, is basically current density multiplied by voltage. It's in milliwatts per centimeter squared as a function of voltage. So you can see the reference curve is here. After spectrum splitting, clearly it has gone up, and we look at the peak values to see how much it has gone up. In both cases, it goes up. For gallium indium phosphide, it goes up a lot more than gallium arsenide because of the higher voltage. And the total power output predicted to increase by 28%. So what that means is that by doing spectrum splitting, you can increase the total power output by 28% compared to the case without spectrum splitting, but using the same two cells. So that's the picture, and those are measurements we've seen. So this is the same simulation. That's the experiment similar to what you just saw. So I'll kind of go through it fast. That's the efficiency. And this is nice to see because you can kind of visualize what's happening. So that's the device, but the camera is focused on the solar cell, so this is out of focus. But this is the gallium arsenide cell. That's a gallium indium phosphide cell. So what we do is we have these crocodile clips in this order, the contacts on. We measure the IV curve for this, then move over and measure the IV curves for this. Okay, so we measure them separately, one at a time. And this is what we get. So this is the reference, same as before. This is the measured under spectrum splitting, same gallium indium phosphide, gallium arsenide. Clearly, there's an increase. The current density increases, but not as much as the simulation. If you recall, the simulation was down here. It's a little bit less. Same thing here for the gallium arsenide. So also the increase in the open circuit voltage is not as high as we expected. Nevertheless, the trend is correct. You can also look at the measured power voltage curve. So that also increases. So the peak power increased. But the total output is increased by 16%, not 28% as we had expected. And the reason for that, I won't go into it, but a lot of it has to do with experimental errors. So actually, there's a curve, some data here which has to do with some, errors in our the models, as well as some problems with the fabrication. I won't go into the details of that. It's not super important for us. So just to conclude, in this particular implementation of spectrum splitting, we were able to get about 16%, predicted about 20 to 28%. So the obvious question is, what sort of efficiency is possible? Like, how much could we do this? This question was answered actually by a person called Henry in 1980s, early 1980s. He was working at Bell Labs, and he did this analysis of what happens to the efficiency as you increase the number of bands that you're splitting. In his particular case, he was doing a thermodynamic analysis, a very, very interesting paper. And in that case, so this is showing, this curve is a little bit complicated. Basically, it's showing the cumulative photon count. So this is the number of photons as a function of energy. So it's saying, okay, if my energy is 0, how many photons are there? It's all the photons, right? So all the photons of energy more than 0 in the solar spectrum. And as I increase the energy, the number of photons decreases. So there are fewer photons that with energy 2 electron volts or lower, and so on. And then he's trying to split this among bands. So this is using, okay, if I have 3 bands, what is the efficiency I'll get, and so on and so forth. So I won't go into great detail here, but the answer is kind of summarized in this circle. Here he assumed the concentration factor of 1,000. Okay, it's called 1,000 suns, but it's 1,000. So 1 band gap, the ideal efficiency is about 37%. His number is a little bit higher than most accepted numbers. It depends on how you do the analysis. It's a little higher because also of the concentration here, 1,000. 2 band gaps, you get 50%, 3 band gaps, 56%, and on the other extreme of 36 band gaps is 72%. That's pretty incredible if you can get 72%, right? But of course, 36 band gaps is it's almost impossible, I would say, today. We can, so the question really is, if you think about it, how could we ever get to solar cells that are 50% efficient, which is a good goal to have. This is probably one of the best approaches. Okay, we can either make, 2, 3, 4 band gap materials, or you can do spectrum splitting with 3, 4 bands. So this is showing 4 bands. Then obviously your question is, okay, what is the best we've done so far? We've done with 3 cells in my lab, and the efficiency we gain is not that high because our cells were not very good, but we showed an improvement of or increase in total output power of about 35%, which is pretty good. But the absolute efficiency, as I said in the last lecture, is very, very hard to characterize. We had to send our system to the National Renewable Energy Labs for certification. That hasn't been done yet. In any case, so that's basically my last slide, and I'm going to end here. So first of all, let me stop and see if there are any questions about all the things I talked about. It's a new topic, and I want you to kind of just appreciate, that efficiency is just to summarize, efficiency is very important. The second thing is, one of the big reasons for why efficiency is lower than what we would like is because of absorption and thermalization. In other words, the solar spectrum does not match the band gap. So, and there are 2 different approaches to overcome this. One is to use multi-junction solar cells, and 2 is to do spectrum splitting. And I gave you an example of spectrum splitting approach that we do in my lab. I want you to think about in a homework of other approaches that you can do. In fact, one of the first times I taught this class, one of the projects that the students worked on was a very, very simple form of spectrum splitting. And they actually built it and did some very simple experiments. And you can, of course, think about it yourself. Great, so I'll stop here. I know Apratim wants to go through the last problem, but if there are any questions, happy to answer them now.
You can, document can hear. You can ask it.
The polychromat, is that something your lab is looking into, or is there like a company that manufactures that?
No, there is no company that manufactures it yet. Yeah, this is just something we make in the lab. We are trying. We are trying to commercialize it. So for other applications, not really for solar. For this is actually interesting to this group because we started actually had a spin-off company trying to commercialize this for solar. This was maybe 5 years ago, maybe 6, 7 years ago, let's say. Unfortunately, a couple of years after we tried, the market really crashed for solar. In other words, the cost of solar cells went down drastically. Then it did not make sense well, there was no business case for it. So that's an example of, and the company was folded, but that's a good example of how the technology is not the only driver, obviously. You also need a market pull for these things to be commercial. And it's a complex answer, but that's a different discussion. If you want to learn more, of course, there's a bunch of papers. Just email me. I'm happy to let you know. Provide them. Great. So, well, I will stop here, but just remind you to keep the schedule in mind. We have about 2 weeks for assignment 3, which is pretty critical assignment. So I hope everyone's making progress. And if you have any questions, make sure you ask me.